The two-person bargaining problem is a problem of understanding how two agents should cooperate when non-cooperation leads to Pareto-inefficient results. It is in essence an equilibrium selection problem. Many games have multiple equilibria with varying payoffs for each player, forcing the players to negotiate on which equilibrium to target. Solutions to bargaining come in two flavors: an axiomatic approach where desired properties of a solution are satisfied, and a strategic approach where the bargaining procedure is modeled in detail as a sequential game. The bargaining game. The bargaining game or Nash bargaining game is a simple two-player game used to model bargaining interactions. In the Nash bargaining game, the two players demand a portion of some good. If the total amount requested by the players is less than that available, both players get their request. If their total request is greater than that available, neither player gets their request. A Nash bargaining solution is a Pareto-efficient solution to a Nash bargaining game. According to Walker, Nash's bargaining solution was shown by John Hisani to be the same as Zeuthan's solution of the bargaining problem. Formal description. A two-person bargain problem consists of a feasibility set, a closed convex subset of the elements of which are interpreted as agreements. Set is convex because an agreement could take the form of a correlated combination of other agreements. A disagreement, or threat, point, wherein are the respective payoffs to player 1 and player 2. The problem is non-trivial if agreements in are better for both parties than the disagreement. The goal of bargaining is to choose the feasible agreement in that could result from negotiations. Feasibility set. Which agreements are feasible depends on whether bargaining is mediated by an additional party. When binding contracts are allowed, any joint action is playable, and the feasibility set consists of all attainable payoffs better than the disagreement point. When binding contracts are unavailable, the players can defect, and the feasibility set is composed of correlated equilibria. Since these outcomes require no exogenous enforcement. Disagreement point. The disagreement point is the value the players can expect to receive if negotiations break down. This could be some focal equilibrium that both players could expect to play. This point directly affects the bargaining solution, however, so it stands to reason that each player should attempt to choose his disagreement point in order to maximize his bargaining position. Towards this objective, it is often advantageous to increase one's own disagreement payoff while harming the opponent's disagreement payoff. If threats are viewed as actions, then one can construct a separate game wherein each player chooses a threat and receives a payoff according to the outcome of bargaining. It is known as Nash's variable threat game. Alternatively, each player could play a min-max strategy in case of disagreement, choosing to disregard personal reward in order to hurt the opponent as much as possible should the opponent leave the bargaining table. Equilibrium analysis. Strategies are represented in the Nash bargaining game by a pair X and Y are selected from the interval D, Z, where D is the disagreement point and Z is the total amount of good. If X plus Y is equal to or less than Z, the first player receives X and the second Y. Otherwise both get D. Often, there are many Nash equilibria in the Nash bargaining game. Any X and Y such that X plus Y equals Z is a Nash equilibrium. If either player increases their demand, both players receive nothing. If either reduces their demand, they will receive less than if they had demanded X or Y. There is also a Nash equilibrium where both players demand the entire good. Here both players receive nothing, but neither player can increase their return by unilaterally changing their strategy. Bargaining solutions. Various solutions have been proposed based on slightly different assumptions about what properties are desired for the final agreement point. Nash bargaining solution. John Nash proposed that a solution should satisfy certain axioms, invariant to affine transformations or invariant to equivalent utility representations. Pareto optimality, independence of irrelevant alternatives, symmetry, Nash proved that the solutions satisfying these axioms are exactly the points which maximize the following expression, where U and V are the utility functions of player 1 and player 2, respectively. That is, players act as if they seek to maximize where and are the status quo utilities. The product of the two excess utilities is generally referred to as the Nash product. Intuitively, the solution consists of each player getting her status quo payoff in addition to an equal share of the benefits occurring from cooperation. The Nash bargaining solution can be explained as the result of the following bargaining process. A current agreement, say, is on the table. One of the players, say player 2, can raise an objection. An objection is an alternative agreement. Probably, the alternative agreement is better for player 2. Raising such an objection has some probability of ending the negotiation. This probability can be selected by player 2. The objection is effective only if, i.e., player 2 prefers the alternative agreement with a chance over the original agreement for sure. Player 1 can then raise a counter-objection by claiming that for him, this means that player 1 prefers to insist on the original agreement even if this might blow up the negotiation. Player 1 prefers the original agreement with a chance over the alternative agreement for sure. An agreement is a Nash bargaining solution if, for every objection raised by one of the players, there is a counter-objection by the other player. It is an agreement which is robust to objections. Kalai-Smorodinsky bargaining solution. Independence of irrelevant alternatives can be substituted with a monotonicity condition, as demonstrated by Ehud Kalai and Mir Smorodinsky. It is the point which maintains the ratios of maximal gains. In other words, if player 1 could receive a maximum of with player 2's help, then the Kalai-Smorodinsky bargaining solution would yield the point on the Pareto frontier such that egalitarian bargaining solution. The egalitarian bargaining solution, introduced by Ehud Kalai, is a third solution which drops the condition of scale invariance while including both the axiom of independence of irrelevant alternatives and the axiom of monotonicity. It is the solution which attempts to grant equal gain to both parties. In other words, it is the point which maximizes the minimum payoff among players. Kalai notes that this solution is closely related to the ideas of Don Rawls' comparison table applications. These authors primarily use evolutionary game theory to explain how individuals come to believe that proposing a 50-50 split is the only just solution to the Nash bargaining game. Bargaining solutions and risk aversion. Some economists have studied the effects of risk aversion on the bargaining solution. Compare two similar bargaining problems A and B, where the feasible space and the utility of player 1 remain fixed, but the utility of player 2 is different. Player 2 is more risk-averse in A than in B. Then, the payoff of player 2 in the Nash bargaining solution is smaller in A than in B. However, this is true only if the outcome itself is certain. If the outcome is risky, then a risk-averse player may get a better deal.